Okay, I guess I'll just start now, but like anyway, it'll be recorded. So, okay, so for the coming homework 4, the first problem, I think the first few problems, like I covered that in my last video, which I post in the announcement. So if you haven't watched it, like I would recommend you to like go through that video because that's highly relevant to the first few problems in homework 4. Okay, I'll first talk about the time and or you can say the age of the universe or the age of a galaxy or something like that. So basically, I will first use the look-back time as an example. So I'll show you how to derive that. So basically the actual time in cosmological scale is just like it's always related to cosmic expansion, right? And we know that cosmic expansion is related to like the Hubble parameter, h of h, and or you can say the scale factor or the redshifts. So these parameters are all like related. So, and you can see that all of them are a function of time. Okay, so like you can express h in terms of a or h in terms of z. There are like all mixed together. So like we have h of a, h of z. So if you are asked to calculate a time scale, then a very commonly used approach is to start with the definition of Hubble parameter. So the definition of Hubble parameter is the like a dot over a, right? The derivative of scale factor divided by the scale factor itself. So if we start with this definition, we know that there's a dA dt term in the a dot, right? So that's where the time comes from. So this can be expressed as dA dt over a, right? And if we move around a bit, we will get dt equal dA over h times a, right? So now we can calculate this with integrals. So I'm using look-back time as example. So which means look-back time is the time when like we look back from now to a certain time or a certain redshift, right? So the limit of this integral will be from the time when the light emitted, like at any point we're interested in, to t0, which is the present time. Okay, so, but you can use this like you can calculate this like if you want to know the time from z equal 2 to z equal 1, like you don't necessarily have to like integrate to the time right now. So this can be useful. And the point is always the limit of the integral. Okay, so we'll get dt integral dt equal dA over h times a. And again, like we need to be careful, like the limit of integral. So the emitted time corresponds the scale factor at the emitted scale factor, right, at the emitted point. And then the upper limit would be the scale factor right now, which we know it is just 1, right? Okay, and we can also express this integral in terms of the redshift z. So we know that the relation between a and z is just like a equal 1 over 1 plus z, right? So this integral is just 1 plus z over h, and dA is like we convert a into 1 over 1 plus z, right? And again, the limit of integral. So at the time when the light emitted, it corresponds to a certain redshift, right? Let's say it's Z. And the redshift of present time is when Z equals 0, right? So that's what we got. And okay, so to calculate this, we know the derivative of 1 over 1 plus Z is negative 1 plus Z to the minus 2, right? So this whole integral becomes negative 1 plus Z and 1 plus times 1 plus Z to the minus 2 over H. Okay, so since there's a negative sign in the front, and so we can like switch the upper and lower limit of the integral to from 0 to Z, and that reduced to dz over H multiplied by 1 plus Z. Okay, so with this integral, we can then get the lookback time, which is, we know the integral of dt is like with the boundary, it's just t0 minus t, the time at which the light emitted. And that is what we call the lookback time. Okay, so this thing, we already derived that. It's from 0 to z, dz, and here's the Hubble parameter, h of z times 1 plus z. Okay, so you can find this formula, like you can, like, this is a very commonly seen formula in textbooks, which is the look-back time formula. But this is not like, you can always use this approach to derive any actual time, like from any redshift or to any time, not necessarily for the look-back time. Okay, so for example, I will show you, so you can see there's a Hubble parameter here, right? So we know the Hubble parameter is, the square of Hubble parameter is equal to 8 pi g over 3c squared times rho of t, right? So this is, I think it's also called the Feynman equation. Okay, this is a very important equation in Feynman cosmology. And so let's consider, like, if we are in a matter-dominated universe, so if, let's write it like for a matter-dominated universe, and that means omega m equals 1. So we know that, so I know the professor already covered something like the different components of the universe. And for the density relation of matter, we know that it should be something like rho of t equals some rho 0, rho naught, some constant, divided by a cube, right? And if we express it in terms of z, that would be, oh, sorry. If we express in terms of z, that would be rho 0 times 1 plus z cubed, right? Okay, so if we are in a matter-dominated universe, then we know the density relation is like, is related by a factor of a cubed, right? So that means we can rewrite the Hubble parameter for a matter-dominated universe like h square of t equal h0 squared over a cube for h0 squared times 1 plus z cubed. Okay, and that means we have h of z equal h0 times 1 plus z to the 3/2, right? Okay, so now we can we can plug this into the look-back time equation and see how the time is related to redshift in a matter-dominated universe. So, so now we have T0 minus TE equals integral from 0 to Z, dz over, and the Hubble parameter here is h0 times 1 plus z to the 3/2. And here's another 1 plus z. So we have 1 plus z to the 5/2. Okay, and if you calculate this, you will get something like this. This is a very simple integration, right? It's just related to the 1 plus z to the minus 5/2. Okay. So similarly, you can derive the look-back time equation for a dark energy dominated universe or radiation dominated universe. So if you are still not familiar with the density relation between each component, you can also check out the previous video I posted on Freeman Cosmology, or the professor have already covered that in the lectures as well. Okay, so that's the first part for calculating time scales in cosmic scale. So any questions? Okay, so I know you have done this a lot already in previous homeworks, but you'll need to use this a lot. So that's why I want to cover it again and make sure you know how to do this. Okay, if there's no question for now, I will continue on introducing several different kind of distances that will be used in cosmology. Okay, distance. Okay, so the first one, I'm going to introduce the physical distance, or you can call it the proper distance. Physical or proper distance. So physical distance means that we're actually calculating the proper distance when the light emitted. Okay, so this is a very simple concept. So it's the proper distance is just the proper distance of when light left the object. So it's just c dt, right? And the professor have also covered a bit of this in today's lecture. So the proper distance is related to the co-moving distance by the scale factor, right? So it is equal to a times dr, where dr here is the co-moving distance. Co-moving distance. So by saying co-moving distance, it means that the coordinate grid is growing with the cosmic expansion. So the grid are growing larger and larger with the expansion. Okay, so yeah, this should be pretty straightforward. And next, I'm going to introduce two more commonly used distance in cosmology. So one of them is the luminosity distance. So luminosity distance is defined by the relation between the luminosity and the observed flux, the flux we observe. So I guess you should be familiar with the equation of observed flux, which is equal to the luminosity divided by 4 pi d squared, where this d here is called the luminosity distance. Okay, so just a reminder that the unit for luminosity is energy per time, and the unit for the flux is energy per time per area. Okay, so we have to be careful that this relation like basically assumes that there are nothing between ourselves and the observed object, right? Because if there is anything inside, like between the line of sight that absorbed any lights, then this will not be true, right? Okay. And okay, so the luminosity distance in cosmology is like, we have to make several corrections in cosmology. So if we rewrite this equation, like we have luminosity divided by 4 pi, and for the distance, we just introduce the proper distance, right? So the proper distance is, we should consider the expansion of the universe. So it should be the scale factor multiplied by the co-moving distance, right? So we have A0R squared for distance, but also we need to make some corrections due to the cosmic expansion. So the first one, okay, I'll just write down the real equation. So there should be another 1 plus z squared over here. And the reason is because first we need to consider one of the factor is due to, we know the photon is redshifted because of cosmic expansion, right? So we know the energy of photon is like, the energy of photon is h nu, right? Or hc over lambda. And because of cosmic expansion, the lambda is getting longer and longer, right? The wavelength becomes longer. And that, if the wavelength becomes longer, the energy of photon will be reduced, right? And remember, this luminosity distance equation, the luminosity is related to energy, right? So if the energy is reduced, we have to correct it because the energy of photon is also reduced. Okay, so the first 1 over 1 plus z is because the redshift of photons wavelength. Okay. So how about the second factor? So we can see the luminosity is energy per time, right? So the time rate of photon emission will also affect the distance of this equation, right? So because the universe is expanding, so the photon emission rate will be reduced, right? The emission rate will be lower than a static universe. So this another factor is because of the rate of photon emission. Right. So if we compare the luminosity distance, if we compare the two equations here, we will see that the luminosity distance is equal to A0R multiplied by 1 plus z. Okay. That is the formula for luminosity distance. Okay, and we know that A0 is the scale factor today, and so basically this is just 1, right? Okay, so that's the definition for luminosity distance. And next, I will talk about the angular diameter distance. But before that, any questions so far? Okay, if no, then let's talk about angular diameter distance. So the concept of angular diameter distance is simply that we know if the object is closer to us, then we will think it appears bigger, right? Because the angular size is bigger. But if the object is further away, then it should appear smaller. So that's the concept of this kind of distance. So basically we can see like how large is the size of this object and then infer the object's distance. Okay, so let's draw, like if we observe into the sky and see an object. So let's say this could be a galaxy or anything. And let's say the size of this object is S, and there will be an angle here, right? So this is just this angle will determine how big we think this object is. Okay, so the distance here is defined as the angular diameter distance. Okay, so you all learned before the small angle approximation. So it's a very simple relation that the size of this object, the linear size of this object, is just the distance times the angle here, right? Okay, so, but if we put cosmic expansion into account, then this distance should be, like, as I mentioned before, it should be the scale factor multiplied by the co-moving distance, right? So that's A of t multiplied by r and theta. Okay, so the relation is very simple. So the angular diameter distance is, we can convert the scale factor here to A0 over 1 plus z, right? And then there's a r here. Okay, so yeah, this is the definition for angular diameter distance. And if we compare this with the luminosity distance, we will see that angular diameter distance is not equal to luminosity distance. It is the luminosity distance divided by 1 plus z squared. Okay. And so from your homework 4, I think the second problem, I think you'll be asked to use a formula from the textbook, which is I think is theta equal L times 1 plus C over R. You are asked to use this equation. So basically, this is just the angular diameter distance equation, because so the L here is just the S we're talking about, the size of the object. And then, so this equation will be equal to S over AR, right? And that is what we derived here, right? Because S equal AR times theta, right? So these two are equivalent. Okay, but so another interesting thing is, like, although like intuitively we know that like angular diameter distance should be like the distance should be longer if the object is further away, right? But if you check up, I'm not sure if this is in textbook. I think it should be, and or if you check up on internet, you'll see the angular diameter distance versus the redshift. The relation is like it's not growing, just growing larger and larger. Like it grows to a certain redshift and then start to decay. So that means if we have two objects with the same sizes, it could appear larger beyond a certain redshift. So it's not that the object just looks smaller when it is further away, but beyond a certain redshift, it actually looks larger. Okay. So yeah, so that's the angular diameter distance. And yeah, I think in homework problem, you'll also derive that certain redshift, like what is that certain redshift that makes the object appears largest. Yeah, okay, so that's all for what I want to cover today. Is there any question?
There was none from me. Thank you.
Okay.